Okay, let's jump right into this grade 8 geometry explainer. Today, we're acting as mathematical mystery solvers. Now, if you've been working with transformations lately, you know that two figures are perfectly congruent if one can be obtained from the other by a sequence of rigid motions. Things like rotations, reflections, and translations. But here's the thing. We don't always want to physically move shapes around to prove they match. Instead, we can use specific clues to prove triangles are perfectly congruent. And today, we're zeroing in on three incredibly powerful sets of clues: ASA, AAS, and HL.
Here is our blueprint for today's explainer. 1. Included sides and angles. 2. Angle-side-angle and angle-angle-side. 3. The hypotenuse-leg criterion. And 4. A recap and final challenge.
Section 1. Included sides and angles. Let's get our foundational vocabulary locked in.
To start, I want you to picture the included side as a physical bridge connecting two specific angles. Seriously, if you point to one angle and trace your finger right along the side of the triangle to get to the second angle, you literally just trace the included side. Conversely, the included angle is simply the corner formed right where two given sides meet. Getting a solid grasp on this bridge or corner concept is an absolute prerequisite for the rules we're about to learn, so keep that visual fresh in your mind.
Moving right along to Section 2, angle-side-angle and angle-angle-side congruence criteria.
Notice how the placement of the letter S for side relative to the two angles literally changes everything about which theorem you're applying. For ASA, or angle-side-angle, that blue highlighted side is physically included between the two congruent angles. It's our bridge. But for AAS, or angle-angle-side, that highlighted side is non-included. It's completely outside of those two angles. The sequence of the letters exactly matches the sequence of the parts on the triangle itself. Pretty cool, right?
All right, time for a pause check. Active learning is for sure the best way to cement these concepts. Go ahead and pause the explainer. You've got two triangles here. Both have two known angles and a known side positioned outside of those angles. Ask yourself, is the side the bridge between the angles, or is it on the outside? Which criterion proves these triangles map perfectly onto one another?
Okay, if you deduced AAS, you completely nailed it. The immediate reasoning here is all about location. That known side is clearly non-included. It sits outside our two known angles, rather than connecting them. Therefore, a rigid motion mapping is guaranteed by the angle-angle-side rule, not angle-side-angle.
Section 3. The hypotenuse-leg criterion. And spoiler alert, this one is for right triangles only.
So here's the deal with the hypotenuse-leg, or HL criterion. It has some incredibly strict, non-negotiable requirements. First off, this theorem only applies if you have a right triangle. A verified 90-degree angle is an absolute necessity. If you've got that, you then check if the hypotenuses, those are the longest sides opposite the right angles, are congruent. And finally, check if one corresponding pair of legs is congruent. If all three of these conditions are met, boom, the triangles are congruent by HL.
Let's test those eagle eyes with our second pause check. Take a really close look at these two triangles. They have matching hypotenuses, and matching legs are clearly marked as congruent. But notice, there is no 90-degree square symbol marked in the corners. So, pause the explainer and see if you can apply the HL criterion here. Or, is this a geometrical trap?
Yeah, it's a massive trap. You can never, ever assume a triangle is a right triangle just because it kind of looks like one. Without that verified, clearly marked 90-degree angle, you simply cannot use the HL rule. I don't care how perfectly the hypotenuses and legs came to match up. Always rely on the explicit mathematical markers given to you.
Finally, Section 4. Recap and final challenge. Let's talk real-world application. We've covered some seriously complex ground today, distinguishing between included and non-included parts, and navigating the strict rules of right triangles. So this table gives you a clean, easy-to-read summary of ASA, AAS, and HL. Go ahead and take a mental snapshot of this grid. It ensures you know exactly what clues to look for to guarantee that one triangle can be mapped onto another using rigid motions. Just to recap, ASA requires the side to be the bridge, AAS requires the side to be outside, and HL demands a 90-degree right angle alongside a congruent hypotenuse and leg.
To wrap things up, I'm leaving you with a final transfer challenge. Look at the mathematical modeling flowchart we have here. It guides us from a real-world problem to formulating a model, computing, interpreting, and validating. Now imagine you're standing on the bank of a rushing river.
You urgently need to know the distance straight across, but you obviously don't have a boat. How could you use this modeling process, combined with the congruence rules we just learned, like ASA or AAS, to formulate a triangle on your side of the river that perfectly matches an imaginary one crossing the water? Think about how the geometry on a page actually translates to the massive physical world around us. Until next time, keep looking for the angles.